Welcome back to Office Hours with Dr. Clark. So today we are going to be looking at shapes, molecular geometry, a big deal in general chem, and it sets you up nicely for organic chemistry. So we're going to get right into it. So looking at molecular geometry. So in a previous video, we talked about Lewis structures. So for example, let's take something like carbon dioxide. Now, there's a concept called VSEPR. VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory, called VSEPR for short. So it's a model that explains molecular shape. So what it says that lone pairs are more repulsive than bonded pairs. And triple bonds more repulsive than double bonds, more repulsive than single bonds. So when you have these kind of scenarios in molecules, the electron pairs are gonna try to spread out as far as possible to maximize stability, because electron pairs don't like to be upon each other, right? They want to space out. So let's go back to carbon dioxide. So carbon dioxide, the bond angle is 180 because that's the maximum separation that's going to give us a stable molecule. And we focus on the central atoms when we're talking about VSEPR theory, the shape around the central atom. So a couple of things we want to look at with carbon dioxide. Electron groups, sometimes they're called domains. There are two, because every double bond, every single bond, every lone pair, every triple bond is considered a group. So we have two groups. So the electron geometry is linear. I have no lone pairs around on the carbon, so the molecular geometry will also be linear. Geometry or shape, we call that shape. That's actually, what we could see if we're looking at the molecule is also linear. And we can take it further and say, okay, so since we know the shape, is this a polar molecule? So let's look at electronegativity. So carbon is the carbon bond, carbon oxygen bonds. Oxygen is 3.5, carbon is 2.5. So my delta EN is 1. So that's a polar bond. But based on the shape, since we know it's a linear shape, our dipole moments are going to cancel. So my mu, or my dipole moment, we recall, we think of physics, will cancel. So this is indeed non-polar. All right, so we have our linear. Let's look at the trigonal planar family. So there are two we're going to look at. BCl. So remember, boron is one of those that could have less than 8 electrons and be happy. If you did the formal charge, you see boron is actually 0. Formal charge is really content. We have 3 electron groups. So our electron geometry, geo for short, is trigonoplanar. Our molecular geometry is also trigonoplanar because I have no lone pairs on the central atom. What about the polarity? So the BCl molecule bond, excuse me, is pretty polar. Um, it's definitely going to be the difference going to be more than zero point 0.5 for a difference of electronegativity. Boron is not a very electronegative atom. I think it's about maybe 2.2. Chlorine is 3. So, but there's an equal pull on electron density towards the chlorine. So my dipole moment is 0. So there is an even distribution of electron density. And we could say the same thing about carbon dioxide above. There's some of the terms that we use. Let's look at another trigonoplanar. Let's look at ozone, O3, a molecule that we never really talk about except that, it's being destroyed in the upper atmosphere due to pollution. So if I'm looking at the central oxygen here, my lone pair counts as one group. My single bond is one, my double bond is one. So I have electron groups, there are three. So my electron geometry is still trigonoplanar. I'm just gonna call it trig planar. That's for interest of time. And then my molecular geometry is gonna be different because I have that lone pairs. And the lone pairs, they have more repulsive forces than bonded pairs. So they're gonna be, you know, squashing the bonded pairs, pushing them away. So molecular geometry or shape is bent. So we draw ozone with that bent shape. Let's look at the tetrahedral family. So there are three in the tetrahedral family. So we're going to look at, draw my hand properly, ammonia. So here's a little structure for ammonia. How many electron groups do you have? That's right. 4 electron groups. So my electron geometry is tetrahedral because I have 4 electron groups. My shape or molecular geometry is trigonal pyramidal. Trigonal pyramidal. What about polarity? The nitrogen hydrogen bond is polar, right? So there's a electron density movement towards the nitrogen, and since everything is on an angle, there's going to be a resultant dipole. So my dipole moment is greater than 0, so it's polar. That's the first tetrahedral. Let's look at water. So my electron groups is 4. Electron geometry is tetrahedral. Let's call it tet for short. We get the point of this morning. Shape is bent. What about water? As far as polarity. So we have dipole moments. The OH bond is polar, and they're being pulled on an angle. So we get an overall dipole moment greater than 0. So water is a polar molecule. And the last tetrahedral we look at is methane. So you see, they're all in the tetrahedral family, such that they have different molecular geometry because some have lone pairs and some don't. So in case of CH4, we have how many electron groups? And four. Electron geometry is tetrahedral again, but the shape is also tetrahedral because I have no lone pairs. What about the polarity for methane? So the carbon-hydrogen bond, the CH bond is nonpolar because the electronegativity difference is less than 0.5. So since no bond in here is polar, then the molecule, the dipole moment is equal to zero. It's a nonpolar molecule. So there are like a lot of the shapes. So we're going to look at two more. One being trigonal bipyramidal. This kind of show you what happens if you have one of those mo molecules that have molecules that have 5 atoms around the central atom. But again, we're focusing on the phosphorus as being the central atom. There are 5 electron groups. Electron geometry is trigonal bipyramidal. And the shape is also trigonal bipyramidal. Bipyramidal. Right. It's almost like you have two pyramids, like their bases facing each other. The polarity, the PCl bond is a polar bond, but there's even distribution of electron density. These two chlorines, the vertical ones, are equally pulling the this the planar Cl here. They're equally pulling, so we get a non-polar molecule. Okay. So the bond angle here is 120. The vertical bond angle is 90. I forgot to mention about tetrahedral. The ideal bond angle is 109.5. So they'll be approximately different tetrahedral will have like somewhere around 109.5. It depends on the lone pairs. So lone pairs are gonna kind of squash water. So your bond angle is gonna be less than 109.5 here. Ammonia likewise because the lone pairs less than 109.5. The more lone pairs, the more compressed the bond angle will be. So water will be less than ammonia, for example. But for most chemistry class, you just need to know it's around. So you don't need to know exactly the exact number. And then the last one we look at is octahedral. Octahedral. That's when I have 6 things around the central atom, like SF6. Three groups. How many around the sulfur? 6. The geometry is octahedral. Shape, also octahedral. All right. So, and there's under trigonal bipyramidal and octahedral, there are several other subshapes, like, depending on how many lone pairs you have around central atom. So we won't get into those. So bond angle here is 90, and that's 90. This is a nonpolar molecule because all the fluorines, the electron density, I mean, the SF bond is very polar, but since I have an equal spread, it's very symmetrical. It's gonna be nonpolar. All right, so my dipole moment is 0. Okay. So the last thing on this video I want to talk about briefly is hybridization. Hybridization. It's a model we use to see, to kind of explain bonding. So for example, if I have a tetrahedral, so all my tetrahedrals, what we're saying is the atomic orbitals combine to form these bonding orbitals called hybrid orbitals. And for the tetrahedral, it's a combination of S and 3 P's, right? So we're not going to get into the electronic version of that, cover that in classes. But what's important is to be able to recognize. So if I have any tetrahedral, anything that falls on a tetrahedral, CH4, NH3, all these have 4 electron groups. Four electron groups. So it's going to be sp3. Right. Trigonal planar. That's a sp2, meaning I have 1 s and 2 p orbitals combined to form the hybrids. Right. So with trigonal planar, we have the introduction of double bonds. So for example, let's look at formaldehyde. 3 electron groups. So it's going to be sp2. And so for sp2, they're unused p orbitals. When you have double bonds, they're unused p orbitals that overlap to form pi bonds. So when you see a double bond is a sigma bond plus 1 pi. So you might say, where is this? So sigma, okay, so to be clear, every single bond is a sigma bond, but your double bond has a sigma and a pi. Let's go back to these. All these are single bonds, and they're called sigma bonds. Electron density is kind of focused, um, flush between the internuclear axis between two atoms, like right in the center. Your pi bonds, however, if I were to draw this molecule here, my pi bonds, this pi bond, double bond, they exist above and below the plane of the molecule. And this this represents, you know, this represents all these this sigma bonds, and then the pi bond, the double bond is a 1 sigma, 1 pi. Okay. So anytime you see a double bond, you want to think of, okay, there's a 1 pi bond, 1 sigma bond. And the hybridization, the bonding occurred because there was an overlap. There was an overlap of atomic orbitals, 1s and 2 of the p's, to form your hybrid orbitals that overlapped with the other atoms to form bonds. Okay? And then the last one we look at is linear. So let's look at acetylene. So linears are sp, 2 electron groups. Same time you count two electron groups around a central atom, we're talking about the central atom. We're focusing on the central atom. We can sometimes look at the outer atoms, like if there's an oxygen, you can say, okay, well, that's also some hybridization, but let's focus on the central atoms. And you'll see here, there, around each carbon, there's two electron groups. One here, one here. Right. So so 1s, 1p is combined to form the sp hybrid orbitals, and then they are responsible for bonding. So we get that linear, that 180 degrees. Right. But now there are two unused p orbitals that form two pi bonds. So your triple bond is 1 sigma plus 2 pi. So every single bond is a pi bond. I'm sorry, every single bond is a sigma bond. Every triple bond is 1 sigma, 2 pi. So if we were to draw, so we have our sigma in the middle, we have our pi, there's 1 pi above. And let me change the color here. And then on either side, so horizontally, there's also another pi bond. So that's how you get your triple bond. And then you have, let me go back to black here. So then you have your SP, another SP bond here. So that's sigma here, sigma here, sigma in the middle. And then you have pi here as well as pi here. So that's how you get your two pi's. And this is hydrogen. Same time you see a bond, a central atom with only two electron groups, it's going to be an sp hybridization. So before we close, what if we have a molecule with several central atoms? Like let's take something like ethanol and drinking alcohol. Let's label these. So we can look at a lot of details. So we can look at the shape. So we have 4 electron groups. And my electron geometry is tetrahedral. My shape is also tetrahedral. Hybridization is sp, what do you think? 4 electron groups, sp3. It's going to be the same thing for this other carbon. It has 4 electron groups, tetrahedral again, shape tetrahedral. What about this oxygen? It has 4 electron groups. 2 of them are lone pairs. Electron geometry is tet. Shape, however, is bent. And what about hybridization? Well, since I have 4 electron groups, it's going to be sp3. What about the polarity of this molecule? This molecule is indeed polar. Because if you focus on all these bonds right here are nonpolar. Right? So on one side of the molecule, I have a very electronegative atom, which is pulling electron density from everywhere else. So we're going to get a resultant dipole going towards the oxygen. So that is a polar molecule. All right. So that is how you deal with hybridization and also molecular shape and geometry. All right. Until next time, Hafiz, I was Dr. Clark.